let's begin. I had very quickly gone through the matrix multiplication, and I have tried to now put the slides, the code, as much as possible on one slide. As a result of which it has become a little smaller, but I think I can read it from here. So you guys being younger should be able to read from wherever you are. Okay. So we decided that this is not the only way, right? In fact, we will discuss what are other alternatives you might have chosen. You want, in this case, one thread to compute one element of the resulting product matrix. Okay, and just to make sure we understand the parameters, we are doing there is float star n. Those are the two matrices. Each is width cross width, and we take m times n and produce the result in P. So this host function is being passed these parameters, right? To enough space to store the result of these two input matrices product and the size of the two matrices along with the matrices. And we decided that for every element of the output, one thread is going to create that output. This will not work when the number of elements that you need to produce is more than the number of threads you can keep in a block. Okay. So if you're multiplying two big matrices or bigger matrices, then you've got to do something else. All right. So that something else we'll discuss after we take the simpler case. So in the simple case, we have one entire row of m and one entire column of n being read by one thread. Okay. We realize that the same row is also being read by other threads, and the same column is also being read by some other threads. And so there may be additional reading we are potentially doing here. Okay. But again, to keep things simple, we have allocated space on the device. Those are the variables pointed to by MD, ND, and PD. We do CUDA malloc on each of them to get enough space such that the input matrices can be passed on from the host and the output matrix can be produced on the device and then passed back on. So CUDA malloc creates that matrix. CUDA malloc is something you have again to do on the host so that the mallocing is happening on the device, and you would do this when you need this pointer on the host, right? If you want to do regular malloc on the device, that pointer is not going to be accessible by the host. Then CUDA mem copy takes your float pointer from where you are copying. For example, in the first mem copy call, that's m. The device handle, right? It's not a real pointer. Device handle that has been returned in the float pointer that you were referring to as MD, and the size. How many elements did you want to copy? The size should be calculated from the width. I am doing it? Where? Oh, yeah, right. So it's calculated from the width in number of bytes. Then you call the kernel. Right? This is the host code, so there is this number 2, which is the kernel invocation, which will come later, and the kernel itself, which will come later. And at the end of it, you mem copy the result. Right? If for some reason the two variables MD and ND have been modified on the device, which in this case it won't be, then and you wanted those modifications back, then you would copy them back also. And then CUDA free. Okay. This is the kernel function, which would take something similar to what a regular host matrix multiplication function would take, right? Kernel function is something that each thread is executing. Okay, so it needs a pointer to the 3 matrices, right? And the width. So as a thread, what would you be doing? You know that you have to produce one element of the output. You would first figure out which element of the output you are producing, right? If you recall the regular host matrix multiplication loop, then there is an I that goes from 0 to n, there is a j that goes from 0 to n, and ij is what you are producing, and then the k also goes from 0 to n to produce each ij. Right? So now you're saying which ij am I, then I'm going to go loop over k. Right? So which ij you are will be given by your thread ID. Okay. If you have generated, so width, cross width block of threads, then you get your y index and x index, it tells you your I and j. So to figure out where to read, so this is where your DD will go, right? Your index. What are the MD and ND, row numbers and column numbers? Again, your index.
So here we are using only one block?
Yes. So your index tells you that row and that column. How do you get the elements of that row now? If it is a row, then you would just go 1 plus 1 plus 1 plus 1. If it's a column, because we haven't declared the MD and ND as an array, CUDA array, which will be 2D array or 3D array. We have declared it to be a regular pointer. So now we have to figure out the address. So we'll figure out the address based on your ij. You know the width, so it's easy to do. You take this in a loop. So k goes from 0 to width. You keep varying the address you're fetching the element from, the address you're fetching the element from, multiplying them and adding it to your partial result. And once you're done, you put your number in the proper place in PD. Right? If PD were a 2D array, then you would say my index y, my index j, my index y, my index x. Because it's a 1D array, again you have to compute the address of it. And how do you call it? So this is the host code again. And I'm going to try to fit in the number 2 in the same by making the other stuff smaller, which we have looked at before. So you're going to call that kernel, same name that we saw earlier, with dimension of the grid and dimension of the block. And dimension of the grid is declared to be a 1 by 1 thing, and dimension of a block is declared to be a width by width thing. There's no shared memory being used here, so you don't say I want so many bytes of shared memory. And then you send the 3 pointers and the width. The parameters that you send here will get populated by the proper pointers on the device side. All right, so this is how you would do, you would manage if there is only one, not necessarily one SM. If you have small enough number of rows and columns that you don't exceed the block size, the maximum block size. Okay. But before we do that, what can you do to reduce the number of reads? How many total reads are happening here? 2 n cube. And should there be 2 n cube reads? 2 n squared? Should there be 2 n squared reads? Okay. Should there be 2 n cube reads?
There would definitely be 2 n squared reads.
Well, there are 2n squared elements in unique, potentially unique elements. So you have to read them. But each element is being read by everybody who's handling that row. Right? And n people are handling that. So if you copy that row, that entire row once to shared memory, then you will be reading from shared memory. You'll still be reading n cube times.
Latency will be much less.
Yes, but your reads will get faster. Total number of reads, this plus that, is actually going to go up. Usually that will be a good thing.
But shared memory is small, I mean very small.
Shared memory is small. But in this case, since we are assuming that this block fits, this block is also small. The matrix is also small. Okay, so now if the block doesn't fit.
So is there any mechanic to directly put the block into the shared memory instead of putting it into the into the program?
No. The host doesn't see shared memory. It's like a local cache for each of the processor, and each has its own copy of shared memory. So it would be complicated for a host to say put it in that shared memory, and that shared memory, and that shared memory. Okay. So what if now the matrix size is bigger? Doesn't fit into one block, so you have to have more blocks. So again, there are probably many ways in which you can break the problem down. One, maybe you subdivide your block, your output matrix into blocks of the size that you can handle, and then you produce one block at a time. Each thread block produces one block of the output matrix. All right. So now that block is going to read all the blocks in a row in one matrix, all the blocks in its column in the other matrix, and then do the same thing. But again, there is repetition within a block. There's nothing you can do about repetition across the block because there is no real synchrony that you can maintain across blocks. But within a block, you can still bring it in the shared memory and read then from the shared memory whatever you are requiring. Something that we will talk a little bit later in more detail about is that when you read, when that kernel or that threads within a block are all reading, what kinds of memory access are we generating? For example, let's go back to that loop of the kernel again. For k is equal to 0 to width, you as a thread are saying read this, read that, take the product, accumulate. Right? At the same time, another thread, at least the ones within your warp, are doing the same thing. Right? And as long as other threads within the warp are near you, right, which it would be because you're saying your block ID, which goes from I is equal to 0 to width, j is equal to 0 to width, is basically the way you are dividing your matrix responsibility also, the output matrix responsibility. Then the IDs within a warp will go from k to k plus 31. And unless this dimension of the matrix is odd, there will be one chunk of rows in it, one chunk of columns in some row. Okay. If the matrix is 17 by 17, what will happen? So 16, so the warps are 32, right? So 32, right? And if you have, well, 17 is probably a small number, let's pick a bigger number, 35. Then you get 32, and then the next warp of 32 is going to be doing something over here and then something over here. Okay, so the coherence will be lost. And so it's a good idea to organize your data in the way you would expect the warps to be organized. Okay, and sometimes it is more useful or more advantageous to let few of these elements, the threads, not do anything. For example, if you had to have 33 is probably a wrong number. Suppose you had to have 31. Then instead of the 32nd element of the warp going to the next row, you would let 32nd element do nothing. Okay, so that the next row again remains aligned. And so when you are looking at both structuring your computation and making data structures, the structs, alignment is something you will want to keep in mind. Right? Things are generally okay, good, if they are in multiples of 16, 32. Typically on a CPU, things are good if they are multiples of 4. Here, that granularity is somewhat big. So we can get a block multiplied. What happens if can there still be a problem? Then you'll have to break. Right? Then you'll have to say I'll accumulate partial results for just this chunk, while as my neighbor is also accumulating partial results for the same chunk. So there's some complication in code that you'll have to bring in to account for it. But right now I'm not using shared memory at all. Just for simplification, directly doing this on global memory. Even the size of grid is limited, right, by the size of short, 65,535. So if your matrix size is 65,535 times 512 or 1024, whatever that limit is for the given architecture in each dimension, then one kernel call will not do it. So then you will say, I'm going to write multiple kernels, and each kernel will produce one segment of my output. That segment is no bigger than 65,535.
Can you not say that the same thread will compute multiple elements?
We can do that. Yeah, that was the next thing I was going to ask. What is the difference between the two?
So the second kernel has to wait till the first kernel gets done, right? But
in 1.x, compute capability 1.x, that is the case. 2.x, that is not the case. Moreover, I've mentioned this notion of streams. Right? You can create streams, and then multiple streams can have ongoing kernels. So starting off kernels is not necessarily an issue. As a CPU, you can give all the kernels on and say, now let's wait for them to get done.
so the global memory is it persistent among? I mean, if I run one kernel, then run the other kernel.
Yes, it is consistent. It is persistent.
will not accumulate the whole matrices if they're that large. The global memory is like 512 MB. So if you have a matrix which is that huge, which is eating up everything in the processors, then it may also not fit on the global memory.
That is one issue. Although now you can get 6 gigabytes of global memory and probably 8 coming soon.
This is not a problem. The size of the global memory should not be assumed.
It can be a problem, right? It's something to be aware of. But there is also an issue of, in fact, let's back up. When we broke a kernel, which was one block for the entire computation, into some k1 by k2 blocks, because one block couldn't do everything. Couldn't we have done the same thing? Couldn't we have said, let one thread compute a block of output rather than one output?
Wasting the other processes, other SMs. So the block would run on your mod.
So one block is limited to one SM. So if you have multiple SMs, then you are going to want to run enough blocks, right? As a matter of fact, even if you have one SM, you probably want to run enough blocks. Okay, at least you definitely want to run enough threads, which means enough warps. And enough warps doesn't mean 1 or 2. Enough warps means something in the order of 16 to 32 warps. Okay, so if your block size is big enough, 32 warps of block, 32 warps worth of a block, which you can do on the 2.x, it's probably okay. But you would want many warps, potentially many blocks, on each SM, and you would want at least that number multiplied by at least as many SMs as you have. But once you go beyond that, you don't get the benefit of having lots of available warps to run. Right? What is the benefit of having 32 warps? If one warp is reading something from the global memory, some other warp's result has arrived, and its product can now be computed. If you have enough so that all of these downtimes, when you're waiting for others' data to arrive, somebody's data has already come in. After that, there is not much further benefit to be gained by having extra warps. Extra warps waiting to run. In fact, in principle, at any given clock cycle, you need exactly one warp waiting to run. Modulo sometimes you can run 2 warps at a time. Modulo those efficiency type issues. As long as the number of warps you can run at any given clock instant are available, then you don't need more. You just need to have enough so that a small fraction of them will be ready to run, hopefully, every clock.
So, do I have control over
what threads go in what warp?
Because that will become important, because I want the same warp to access the same kind of memory locations with it.
That's up to you. The only thing that the system does for you is it generates that many threads and it assigns to them hard-coded thread IDs. Hard-coded meaning predetermined, right? So if you made a 1D block, then threads will go, thread 0 will be running on processor 0. That is also known, but of no particular value to you. Then thread 1, thread 2, thread 3 onwards. What thread 3 does is up to you. So what you do with that IDX variable is up to you. 0 to 15 will always be in a warp. Right? So the 0 to 31 and any multiple of 32 will be in the warp. And even there, 0 to 15 will be half warp, one half warp, and 16 to 31 will be the other half warp. All right. So now, when you do have multiple blocks or multiple threads within a block, there has to be some way to synchronize them. Okay. So far, the way CUDA has evolved, you really have first-class citizens as far as synchronization is concerned, only within a block. Okay, so threads within a block can synchronize themselves with each other. And that's the main synchronization method is called sync threads. It's like a barrier. Its group is your current block, and everybody must call sync threads, just like we have seen before. So if somebody is in an if condition which skips the sync thread, then you're in trouble. It's a little bit stronger than sync threads in that all your memory accesses that you have made before that, in particular all the writes you have done before the sync threads, are guaranteed to have completed before you proceed from sync threads. Right? So it's also a flush of all your memory writes. Okay? Shared memory as well as global memory.
So this global memory flush is concerned only with the block, the threads in the block.
It is a flush, right? So as far as the system is concerned, and when each one goes out, the global memory has that piece of data. Right? There is a common global memory. It's not replicated or anything like you would in a database. So there's one address where that everybody says, I have written something and it should be there. Of course, I wrote it at this time and I don't know when it's going to get to the memory. After I've come across the sync thread, it is in the memory. That's something you can rely on.
So this is offering synchronization of the global memory across blocks.
Yes, right? But don't think of it that way. In that you have no idea what the other block, where it would be. So as a program's control is concerned, you can't rely on that fact. It's just that from the system's point of view, this thing has been done. So you can really only make sure that, or you can only assume this for the rest of the threads within your block. If somebody else has written something to the data you are interested in, you know that it's there now. There is sync threads with certain variants. For example, you can give it a predicate, give it an integer. Right? Think of it as a predicate, and then among all the threads of the block, there's some commonality in that integer can be evaluated. Okay. For example, you can, if you use the standard sync threads, then it does with predicate. Right? So the second call in the slide, it will do sync thread. Right? Everybody is going to come to the barrier, but it will also return a value, which will be how many calls. Everybody has to call sync thread, right? And everybody is calling the same version of sync thread. So sync thread, some predicate is being called by all the threads of the block. And you can know if everybody called with a 0 or not. So it's really a Boolean. It's taking an int, you can imagine it as a Boolean. And if everybody's, not everybody's value is 0, but how many people's value is 0? You can get a counting version in this case. And there is an and or, which says if everybody or anybody is not equal to 0. Unfortunately, the interesting versions are only available on 2.x, as you might have guessed. There are also some special synchronizations that you can do within a block. Right? Although if block is in lockstep fashion, there are certain things you may want to know about other threads that are executing with you at a given time. And we are going to take a quick break for changing of the slide, and then I'll tell you, think about what kinds of things you might want to know about other threads that are in the SIMD in lockstep with you. Ex modulo conditionals, like sometimes people may be diverging because of branches. So let's continue. Yeah, go ahead.
So it can be used as a reduce function, right? In some sense, this sync predicate.
It is only a Boolean, right? It only tells you, let's look at the slide again.
What is it depicting us? What exactly it's telling us? It's just telling how many, each one of this has this variable.
So typically in sync threads, you just know that everybody came to this point, right? Now suppose people come to this point with an agenda. Right? I say I want to do X or Y. Then you can figure out people's agenda. Something about people's agenda, not everybody's agenda. You can ask how many people are coming with a positive agenda. Right? Or you can ask, is everybody coming with a positive agenda? Or is anybody coming with a positive agenda? So it's really those variants.
So it has to be a variable, it can't be an expression. The predicate can't be an expression.
Yes, it can be. Yeah, it's a value, right? That expression will be evaluated and then passed to the function call.
Boolean.
Well, it's the C Boolean, right? So if it's an integer, and Boolean true false means not zero, non-zero. Anything that's not equal to 0 is true.
No, you can use it in a logic, right?
You can use it in a logic, yes. Yeah. You can count number of ones within your block. Yeah. Okay. So what kinds of things would these kinds of things be also useful within a warp? Warp. In warp, you don't need to have a notion of sync, right? Because you are kind of in sync. But you may still want to know if everybody has a positive agenda. Right? You may want to agree on doing something. Sometimes you are cooperating, right? You are not just doing independent things. You may want to decide, should we go ahead? We are all computing something and you want to do an early exit. If everybody has decided that there's no point going forward, then you can quit. Right? Everybody can quit. If anybody says it's okay to quit, maybe it's okay to quit. Or if everybody says it's okay to quit, maybe then it's okay to quit. So those kinds of things is why this predicate thing is there. And for warp, within a warp, you can still do all and any, or it's called ballot, right? Which is a bit more rich. It's not just counting how many people are coming with a positive agenda. Right? It's giving you a bit pattern of who is coming with a positive agenda. Right? You've got a 32-bit integer you're passing, and there are 32 people in the warp. It's going to tell you which of them had a non-zero predicate. That bit will be turned on. So everybody can determine who is voting yes, who is voting no. And then based on that, they can choose to do different things. The ballot is only supported on 2.x. Okay? All and any are supported, I think, on all of them.
Operations would require hardware support for them to be faster.
These all require hardware support. Yes. Right. Especially the ballot one. Ballot one is rather complicated. What about the memory consistency? synchronization on the memory.
Sync thread is already
Only within a block.
If some memory access is pending, then the walk will not be called at the other walk will be
That's for a read, right? When you issued a read and your data hasn't come yet, then you can't get your next instruction scheduled. If you issued a write, you can go ahead and do something else. Okay. There are atomic operations on memory. Right? Either you can lock, and full-scale locks really are not provided. At least at the hardware level. Even on the CPUs, you typically only get OS implementing the variety of mutual exclusion methods. So at the hardware level, basic locking on memory locations is provided. So, and to expose that, there are instructions in the PTX as well as function calls that translate to those instructions, which say modify something, add something to this variable directly in memory, right? Add 1 to increment this variable. So, which would otherwise mean read the current value, add 1, write the result. Now it is increment this memory location, meaning that if two people are incrementing or even reading, you make sure that you don't between them, whichever occurs first is up to you. But once your increment has started, right, nobody is going to read the variable until you have updated. Okay, and so there are various. You can look up the list. You can find. You can add things to it. You can subtract things to it. You can multiply atomically. You can swap a value with the register value with the memory location atomically. That's what atomic exchange function is. You can take the min of a register value and a memory value atomically and things of that sort. Most of these atomic operations are actually designed for 32-bit integer operands. Okay. Eventually, they got also upgraded to 64-bit operands, but still integer, right? Long. The 2.x has further generalized it, so you can actually add two floating point things also in an atomic way. But in 1.x you can only add integer things, increment integer things, add integer things, and so on and so forth. The exchange of a register and a variable, because that's kind of type free, is allowed on all 1.x or 2.x, but that's exchange is in some sense the only exception. But they all provide this atomic gas, which for compare and set. Okay. If you have done an OS course, you have seen either compare and set or some version of compare and set. What does it do? This is a prerequisite. You should know compare and set. It is definitely one of the ways of implementing. Sorry?
You stick to check the bit is set or not, and then the bit is 0.
That's a very restricted kind of compare and set, but it really is you compare, you provide an address and you provide a value, right? And if that address is equal to this value, then your new value can be put in there. Okay, that's the standard compare and set. If it is not equal to this value, then that memory location does not get updated. Sometimes as a side effect, you get that old value back. If it is not equal, if it got written, then you know your value got written. It meaning that the old value was what you were comparing against.
It is used to implement star.
It's used for many lock-free algorithms. We'll talk about those also later on. Right? You don't have to physically lock a resource as you do for a critical section normally and unlock it. It is a locking of sorts, but at a very, very fine granularity. And so we'll use compare and set to do lock-free synchronization later on. Remember, we talked about memory being mapped, right? You are addressing the same memory on the host as well as on the GPU. And if you're performing an atomic operation on the GPU, host in the meantime can also be writing to it, right? And because host really isn't physically writing to the same location, it's writing to a proxy, how they interact with each other is not well defined. Right? It could be done, but then atomic operations will become extremely slow. It has to then synchronize with the host also. And so it's not provided. It says that you make sure that the host is not operating by whatever means you otherwise figure out. This is an atomic operation only from the GPU's point of view, in the context of the GPU. So if there is some other GPU operation on that memory location, that will get logged out for that small period. Okay, here is an example of CAS. It's called atomic CAS, the function. In this case, atomic CAS is being used to do double operation. So I said that you can't take floating point things and add together, add with another floating. So there is no atomic add on floating point values except in 2.x. And even in 2.x there is no atomic add on double values. Okay, but you can use compare and set to implement all other kinds of atomic adds. In fact, CUDA didn't even need to provide all these different varieties of atomic functions because they can be simulated, they can be done by compare and set. So how will this work? And here there is a little bit of lingo here. Don't worry too much about double as long. It's really a cast of taking a double and thinking of it as a 64-bit integer. And similarly, long as double is the opposite of that. Take 64-bit integer and interpret it as a double in an architecture independent way. So this is a device function. It wants to add a value atomically to this address. Okay, and nobody should be able to do something in the middle. So why should this work? What is happening here?
It's a spin lock, so you continuously read it.
It is a spin lock. That is something, unless you have some other thing, you can do some other things also in the meantime. But compare and set are typically spin lock style. It is, you should more equate it rather than with spin lock style with a lock which is non-blocking. You're trying to lock, and if you didn't get the lock, you go do some other thing. You're told that this lock is not available. But if you have nothing better to do, then you'll spin lock.
But this is really just that, right?
This is spin locking. So what does this call provide you? So basically, what are you trying to avoid? You're trying to avoid, typically what do? You read the value, add the thing you want to add, and then write the result.
Basically, there is some context switch after zooming into old. with making sure that the content at the address.
It's not about context switch per se, but it's the logic remains the same because there's somebody else doing it at the same time. Go ahead.
The content at the place address means simultaneously two threads are changing it. So I should be sure that while I'm storing it in assume, then it might happen that that after this I'm storing it and then other thread changes it. I want to make sure that it remains same throughout this operation.
Right. Right. So I read a value, I add something to it, and now I'm going to write it. But I want to write it in a way that I ensure that nobody else has come along and modified the value in the interim. Right? That's what atomic add would have done. Right? It would have logged everybody out right here. But since I couldn't do that, I've read it, I have added the thing I wanted to add. Before writing, I check, is it still the same? If it is still the same, that means nobody has done anything with it, atomically changed it to the new value and go on. Otherwise, somebody has come and maybe done something with it and my old value has become stale. I have to reread. I reread and do the same thing. If this time nobody else came in the interim, then I succeed. Otherwise, I continue doing this. Okay. This can potentially go on forever. It is in some sense similar to atomic add. Right? Atomic add also is trying to acquire a lock to that memory location and then modifying it. Right? So if I can't acquire a lock because every time I go to acquire a lock, somebody else gets the lock.
But some works get done even if someone else requires a lock.
But here also, the reason it has changed is somebody else read it and did something. So it's not that it's busy wait for no reason. It is typically you will not be looping here, right? It's a loop just so if you fail, you're going to retry. But it's not a lock type loop where you say I'm locked out and I keep checking the lock until somebody releases it. It's not that kind of loop. It's a loop that says I'm going to go and do it, but just at the time of doing it, I'll check whether I'm doing the right thing or not. If I'm not, then somebody else has done something else and I should go and redo it. Okay, let's go quickly through some of the things you might want to try if you haven't already. There is a device emulation mode. Somebody was asking me, what if I don't have CUDA card on my machine? CUDA SDKs will work with device emulation mode. It will give you some fair idea of whether your code is grossly right or not. There are lots of problems that it's not going to catch. Primarily because the timings are very different. Also, there are differences in the hardware, especially in the 1.x hardware. Floating point denorm operations are different from Intel's denorm operations. As a result of which, if you're doing anything that requires denorm, then is going to be different. You can use regular GDB, not CUDA GDB, to compile this, to debug this. But again, you have to be careful about some of the caveats. Race conditions are, unless you have designed it very carefully, are normally there in a parallel program. And so they will probably not get caught if you're running in the emulation mode. And there are some things that happen within a block. So the synchronization will behave somewhat differently, and some of them are not even implemented. For example, in fact, this is, I haven't checked if they have updated it. Until CUDA 2.0, I think, the voting within a warp was not properly emulated on the CPU, or correctly emulated on the CPU. There was a bug in it. All right, there are other things. There is something called a thrust template library that you may use. This is not for your assignment. This is if you are going to do a CUDA project, because it has a reduce and you can't use it. You have to implement your own reduce. There is a reduce in the examples also, which is actually not going to work for you because it doesn't work for unlimited data. The way this thirst library simplifies things, again, I'm not going to go through the library. I'm just going to give you a feel for what kinds of things you can do with it, or how it simplifies writing CUDA programs at a slight cost of efficiency. It's templated, and you can declare host vectors and device vectors, which is typically what you do, right? You create an array on the host, you create an array on the device, you copy it over, and then you do things on the device. So here you can simply say thrust host vector of type int, initialize it with certain size, right? So in this case, it's saying 2 to the 24 element integer array is being generated on the host called h_vec, and another vector d_vec is going to be initialized, constructed with h_vec, meaning you've just allocated the memory and copied it effectively. So internally somewhere there is a CUDA malloc and a CUDA memcp happening as a result of this. You can also copy parts of it. So you can say copy into the d vector, begin over here, end over here from this host position. And there are several others that you are welcome to go look into. There is also a somewhat older version of not templated library, but commonly used things like reduce, scan, stuff like that, called CUDPP. Some people, you have used both of them, and what's your verdict on which one? Some people think that CUDPP is faster, and they're not right. Sorry?
Thrust is
Actually, they're not wrong either, because for some things Thrust is faster, but for many other things CUDPP is faster. There are also with the SDK that you would typically install and are installed in the systems which you're using. There is something called CUDA utility library, util.h, and it has some basic ease of operation type functions. Again, I'm not going to go into that, but an example is CUDA safe call. So it's a most of the stuff there is macro, not all, but most. So CUDA safe call, you wrap that inside, wrap any CUDA call into this CUDA safe call macro, and it turns it into, if this call succeeds, then do something, otherwise print something. So it's going to, if there is an error in making that call, then you're going to get a message. It's not well supported, so you wouldn't, it's okay to do this when you're learning to program, but this is not what you would want to use long term. Okay, so let me take you through a few code examples before I'm going to talk about the detailed performance related issues.
So this device simulation mode is has been removed from CUDA 3.0.
3.0 doesn't have device simulation mode.
No, only the 2.x versions will be used in that.
Interesting. So now they're completely ruling out people having non-CUDA cards. Here is a simple example. This is a more detailed in some sense, but more complete piece of code. And I'm not going to again go through all the details of it, but just to give you the structure, so you will get used to this style one more time. So what's happening in the beginning, and then there is this is a util macro, cut_device_init, which if you have multiple CUDA cards, then it initializes the proper CUDA card or one of them, unless you control it using the argv. You can set your CUDA program to run on any of the available devices. So what's happening here is that you're creating an array of values on the host using some method called getNextValue, and you're going to copy that array value into D values, which is the device version of the same array, and then you're going to call parallel sort, the kernel parallel sort, to sort that array on the device. And at the end of it, you're going to take the result back out and free the memory in which you had the sorting done. And the values is it's an array in which in-place sorting is being done. It's a regular swap function which we are going to use. And then here is the kernel, which is parallel sort. In the beginning, it's using the shared memory, and so it's using the extern shared style, which means, in fact, something I should have pointed out. If you go back and look at the configuration, the call for invoking the kernel, it says how much shared memory I need. And it says I've got num elements in the array, and int is the size, int sized each element. That many bytes of shared memory I'm going to require per block. And the block is simple. One block which is going to be the size of the array, right? Meaning it's the kind of sorting algorithm where you say I've got n processors working on n elements. So I've said the block size is n being the size of array, and this block is going to get some amount of shared memory so that all of the array can be stored in the shared memory. And so how do you get the data into shared memory? By copying it from D values. Okay. Inside here it's being called values because the formal parameter listed on the kernel is calling it values. And one thread is reading one of the values. Right? Ultimately, they are all going to sort it together. They are all going to access different parts of the array. But they together need to fetch this entire list into this location. Right? So they decide there is n amount of work to be done. There are n of us, so we'll do one each. Okay, so everybody has read something, and then they sync to make sure that that entire array has been brought in. Right? So you can't simply assume that we have read and go on and next start to read things from the shared memory. Okay, so at this point, the entire data is in shared memory. Again, we probably need to stop here.